Okay, so yeah, uh, thank you for the introduction. And today I'm going to talk about the localization of effective action in superstring field theory. So there are actually, um, yeah, so there are actually two stories, just as Ivo has already introduced. Sorry. Yeah, so I'm going to talk about first the open strings because it's simpler, and next I'm going to talk about closed strings, and for the final outlook, I will briefly comment some insights into higher orders. Okay, so let's begin with the motivation of studying this effective action, and that is the marginal deformation of string inside string field theory. Just as Ivo said, this can be characterized as a perturbative problem. So yes, so this kind of marginal deformations of string field theory solutions has actually been done, for example, by Professor Okawa, but in the large Hilbert space formalism. So today I'm not going to talk about that because we are going to use the homotopy algebraic formalism. Firstly, because of the name of the workshop, and second, because it's easier to generalize this into closed strings. So yeah. So now we have a marginal worship operator who gives a sort of tangent vector in the modular space of the vacuum. So it should satisfy the linearized equation motion, which is Q BRST closed. The question we want to answer is that can it be lifted to a, maybe I should stand here. The question that we want to ask is that can it be lifted to a nonlinear stream background? So essentially we expand using a parameter lambda, and we asked the equation of motion of this stream field to be 0. And this can be solved order by order. And at each order, the source term has to be Q closed. So this is actually a cohomological abstraction, and solving for the next field requires the class of this source term vanish. So we take the inner product of it with the cohomological class, and it should vanish. So regarding my the title of my talk, the abstraction that we introduced before is actually the same, formally the same as the effective action as a homotopy transfer. Yeah, sorry. Oh, yeah. So this edge is the original space of stream fields, and then we can homotopy. The homotopy transfer tells us we can transfer this into a smaller. Essentially, we can integrate out all the massive stream fields, and we can obtain effective action on the massless part. So what we do is that we just write the full stream field as part of masses, and this I means the embedding of the cohomological class into the original one, and the massive part. And because in string theory we do not care about massive fits because it's not measurable, then we integrate out this and solve the massive equation of motion using this edge, which can be think of as a propagator. Yeah. And we substitute the solution into the action, we can obtain the effective action, which is in the low energy limit. And the order of lambda n sources is just the obstruction that we talked before, projected on the cohomological class. And this nice structure of effective action can be, you can reference this paper by Irving and other authors. Yeah. Yeah. So let's begin with open strings. And the story in the open strings is that the n equals 2 localization of the cubic obstruction gives us some nice structure on the and some constraint on the moduli of the marginal deformation. And this is what we call the generalized ADHM equations. The name will be explained next. So on the small Hilbert space, this is what Ivo talked before, how we construct the string vertices of open superstrings, and I will just briefly recall. So M1 is the one product which is just a BRST operator, and in the coalgebra notations, the M is the full string field theory product, and it should square to 0. And this M, this capital M, is for superstrings is constructed recursively using the zero mode of C, and omega is the cyclic inner product, and among this recursive construction of a string product, we constantly use the BRST exactness, the BRST exactness in the large Hilbert space of the picture change operators, and it supplies the helps us to get the right picture number in the product. Yes. And the seed solution, the first order solution of marginal deformation that we should keep in mind is of this form. So we have the C ghost and the phi ghost. Then this V 1/2 is the matter field, which is a matter field primary of conformal dimension 1/2. And this 1/2 is actually determined by the condition that it should be BRST closed. And also, because we are talking about more of a stable marginal deformation that we have in mind, so it should be at 0 momentum. So it's not like a plane wave. So it's both 0 momentum and masses. And we keep in mind that the GSO projection. Sorry. Yeah. And just as we said before, we can solve the open string equation of motions by perturbation. So at first order, this is just the Q exact closed condition. And at second term, we have this equation, and at third term, we have this equation. We can solve for those equations, but we can see the cursor is not, okay. We can see the general structure is that there is a source term on the right, and there is a Q exact term on the left. So, which means that the source term has to be also Q exact, right? So this means that its projection on the BRST cohomology should be 0. And only in that condition we can solve for example, psi 2 and psi 3, provided the project source vanishes. And also, it should be BRST closed. But this is already guaranteed by the infinity structure. So we will not worry about that. Mm-hmm. Yeah. To solve, we can just, of course, we can just compute, assuming nothing. And we just compute, but the bad thing about this is this edge, this propagator often requires integral over the modular space. So it's often hard to compute, but in this nice case that we assume enhanced global matter equals to algebra on the worksheet. So it's some specific space-time background. Then we can see that the n equals 2 charge decomposition allows us to avoid the computation of propagators. So assume this enhanced global matter equals to algebra, and this allows us to split every deforming marginal field as 2 parts, the plus part and minus part. The plus and minus means that the charge under this J R symmetry of this equals to algebra. And we also assume that the fields has a regular OPE with the supercurrent. And of course, this enhanced global matter equals 3 algebra dictates that the only non-zero correlators or scattering amplitudes comes from the neutral part. So if we have two operators, if we compute two point functions, then it has to be plus or minus plus. If it's 2 plus, then its total charge is not neutral, and then it computes 0 amplitudes. Yeah. Yeah. So let's first attack this quadratic open string obstruction. And we let V be this, and W. W is exactly what we call the test state or the cohomological class. And these V1 and W1 are the, let's say, super partners of this after we act on the mode of supercurrent on the matter field. And we also use this standard notation of computing poles in OPEs. And if we assume that the matter field of this worldsheet CFD has this regular condition, that the V1 with W1 half, the first order pole is 0, and also the V1 half with W1, the first order pole is also 0. And we can compute, and also the superstring product defined before looks like this. So it's just the P extra chain operators distributed over the 3 outputs and averaged. So with the action of picture channel operator on the vertex operator, and similarly for W, the test state, we can directly compute the OPE projection, and we can see that it's of this form. And hence the eta C residues cancel and the other residues vanish. So we can prove that under this regularity condition, that the open string obstruction, the second order, automatically vanish, which has been shown in the paper of Osmera and also of Luca and Tivo. So we should not worry about this at the second order, at least. Yeah, and also because, only the 2 terms here, we have already shown it has vanished. So let's compute the 3rd term. Yeah, the 3rd term is quite complicated, but once we assume that, once we assume that this with OPE with the supercurrent has no double pole, we can just use the exactness of the picture channel operators and show that this has to be 0. And what follows is quite straightforward. So thus, this second order solution solves can be well defined, and we can solve the second order equation. Yeah. Yeah. So the second order is a very simple question. There is no constraint on the modular space, and there's nothing. But what interesting thing happens in the 3rd order? We can see that we pair the obstruction at the 3rd order with an arbitrary physical state E. So this M3 tilde is just the S matrix at the 3rd order, and schematically we can write it like this. So it consists of both the M3 product and M2 product and the propagators, and you can see the essentially different part of the Feynman graphs. The M3 products means the fundamental 4 vertices, and these propagator terms means that we have an internal leg in the Feynman diagram. And yeah, so The direct calculation would require a modulus integral because we have internal leg. We have to integrate to get the propagator. But as we will show in the following, that localization can reduce these internal legs into OPE data. Yeah. So we start from the simplest, the most simple case where there is no stop assumed in the in the string field theory. So the superstring product are just obtained from the Bell product M2 by using the gauge product, the auxiliary product containing C, and it looks like this. Yeah, and the M3 product is defined this way, where X is the BRST derivation of C. And we insert these identities. These identities are the definition of the M2 product. So we insert this definition in the contact terms and the two propagator trees of amplitude. And the thing is that if we expand X as QC, we are actually entering the large Hilbert space. And in the large Hilbert space, if we want non-zero product, it has to be a saturation of Z0 mode. So, but since there is only one C insertion at each leg, it can actually be moved around each legs. So there is no matter, it doesn't matter which leg we attach the Z0 mode. So actually it can be moved forward, move to other places. But so the problem of moving the picture channel operator is not about moving C, but moving Q. So because there are edge in the expression, if we move Q to other legs, the Q will eventually hit the propagator edge. And from the in the Siegel gauge, we have this edge defined by this relation. So it has a contracting homotopy relation. So we cannot just commute H with Q. It will give us 1 minus P0 term. In the mass, in the generic momentum, we can ignore this P0 because it projects nothing. But here we are considering zero momentum larger deformation, so we have to keep this. And this, as we will see, that is exactly where this constraint of ADHM equations comes from. So, but of course, we still have to keep the identity term, but the identity part actually cancels the M3 contact terms by the A infinity relation. So what we have left is just the P0 part. As a boundary term, the name, we call this boundary term because this P0 actually projects, it's a degenerate point in the modular space. So you can think of colliding two insertions into very close, then we can essentially only the OPE, the single part of the OPE contribute. So that's what we call a boundary term because it's the boundary of the modular space, and hence also the term localization because it only matters on the boundary. Yeah, so we show that this picture changing operator can be moved through the tree at the price of have some boundary term. Yeah, since this Q, every external X is also Q closed. So after we move the Q around, it will eventually hit the one of the external X and get zero. So we have this, we have all the surviving Bell trees of the form of this. So intuitively, this is just moving all the picture changing operators to one leg, and what the price we have to pay is that we have to keep track of the boundary term that localizes at the degenerate point of the modular space. Yeah. So what is it good for? So apparently this just looks more complicated right now. But the good thing is that we have this n equals 2 decomposition for the vertex operator. So if we split the string field as minus, plus and minus parts, again, by the Xi0 mode saturation, we can again move the Xi0 mode, and we can again rewrite the PCO and move Q through each out trees. And we can again, so essentially the picture changing operator attached at the first legs can be moved also to the second legs and to the third legs with the price of keep tracking of all the boundary terms. Yeah, it's the same logic. But what's good about this is that if we compute the picture changed string fields, say, we will have it of this form. The first term is CV1 plus minus, and the second term is of this. But the good thing is that now that we have two conservation laws, the first one is the conservation of the R charge, and the second one is the conservation of the BC ghost charge. So essentially, if we want the correlator to be non-zero, we can see that only this term has the correct BC ghost charge. So only this term can contribute. But this term, the V1 part has neutral R charge. So it provides neutral, so it provides zero R charge in the total correlation function. And this tells us that if we have the X attached, for example, for the first two legs, and the second two legs must have opposite R charge, because the first two terms contribute zero. And of course, with the remaining projection on the localized term on the boundary. And yeah, so the logic is, of course, we can use this. Yeah. So the logic is simple. Now, if we have the form of this, it has to be plus, minus, or minus, plus. And we can move the picture changing operator from the second leg to third leg. And then we have, at this case, this has to be plus because this is already minus, and this has to be minus because this is already plus. But if we further move the picture changing operator from the, sorry. Yeah, it's okay, sorry. If we further move the picture changing operator from the third leg to the fourth leg, of course, every moving comes with the boundary terms, as we commented before. Then we see that because we moved to the fourth leg, then it has to be the third and the second and the third leg has to add up to zero. But this is impossible because they are both minus or both plus. So it means that, yeah, so it means that the propagator term vanishes. So we are only left with the localized terms. Yeah. Okay. I don't think so. Yeah. Yeah. So we show that all the remaining terms are the terms that contains P0, not H. So we don't have to evaluate. We don't have to actually evaluate the propagator H, which is very good because, as we said before, the term of P0 can actually be evaluated using PCOs instead of real correlation functions. Yeah, and that's what we call the vanishing of this condition is what we call the generalized ADHM equations. Yeah, these are the explicit definition of the OPE data that we need for generic CFT, matter CFT. We decompose it into plus and minus parts, and then we can define the OPE of these plus and minus terms. The charge residues are the H1 plus and minus are the same charge OPE products, and H0 is the antisymmetric simple pole residue of opposite charge. And for test state deformation, V tilde, the H tilde is defined similarly. And the vanishing of the third order obstruction just looks like this because it's already done, it's already localized, let's say. And if the two-point pairing is non-degenerate, which is obvious, and we can see that the vanishing of this obstruction is just the vanishing of these coefficients. So it's H1 plus equals H1 minus equals H0 is 0. And they are called the generalized ADHM equations. So these are all abstract. And if we impose this on a specific background, if we consider the marginal deformation of the D3, D-1 boundary CFT, we can write down the matter operators with Chan pattern blocks that comes with the matter CFT. It looks like this. So A mu are the gauge field that lives on D3, and the lowercase a is the D-1 zero modes, and W is the blowing up moduli. And this delta is the twist field because on the D3, D-1 sector, the boundary condition of the string is different. So we have to insert a boundary twist field on the string worksheet. And S is the space-time spin field. Yeah. So if we use this specific background, we can compute the generalized ADHM equation. And in this specific case, it's just the ADHM equation. That's why we call it a generalized ADHM equation. So the vanishing of the three product, the transfer three product, which is just the obstruction, is equivalent to the ADHM constraint, which is just the vanishing of the hyperkähler moment map condition. Yeah, so this is very good. And the takeaway of this open case, open story is that the cubic obstruction depends only on the OPE of matter fields, and the full propagated state is not required. And what we will see for the closed strings is that the closed strings in this sense is even simpler because we can see in the closed string case that even the boundary terms is also vanishing. And let me explain why. And also the background that we deformed is called the Eguchi-Hansen instanton, one of the gravitational instanton. So for the closed string story, it's similar. We replaced the A infinity algebra with L infinity algebra, and the action looks like this. This is the equation of motions and the first few L infinity identities. Yeah, but we have to keep in mind that for a generic string field, we have the level matching condition for the string field because now we have homomorphic and anti-homomorphic sectors. And similarly, the products are defined from the bosonic closed string product by inserting left picture changing data and right picture changing data by a twofold recursive relations. And here we can also expand the marginal deformation solution as a perturbation series and write down the first few equation of motions. Yeah, and similarly, we can also define the obstructions by projecting down to the cohomological class. And the L infinity identities again guarantee that both display sources are Q closed once the lower order equation holds. Yeah. So the example that we have for closed string story is that the orbifold of C2, Z2, and this is defined by acting on the four-dimensional Euclidean space by identifying its one point with minus of its point, yeah, the opposite point. And again, similarly, because we have this identification for the twisted sector, again, we have to change the boundary. We have to insert the boundary twist field instead of a bulk twist field instead of boundary twist field for the twisted sector. And if we want to, because this orbifold action creates a singularity on the original point, if we want to resolve from, if we want to move away from this orbifold singularity point in the moduli space, we can use the this marginal deformation as the tangent vector in the moduli space, which is created by inserting the bulk twist fields in both homomorphic and anti-homomorphic sector. The notation is similar to what we have in the open string case, where delta and delta bar are the twist fields, and W and W bar are the moduli, and S and S bar are the space-time spin fields. Of course, we already know from mathematics that this smooth resolution of this orbifold is the Eguchi-Hanson gravitational instantons. But we don't know if a priori the string theory should give the same resolution. That's essentially what this equation of motion determines. Yeah, so again, let's analyze the quadratic obstruction. Yeah, so, but the simplicity of the closed string obstruction is that actually at the second order, the vertex of closed string field theory somehow factorizes into, because there is essentially no Xi insertion in the second product. So it actually only PCO insertions, and it simply factorizes into holomorphic and anti-holomorphic sectors like this. And we already showed that in the open string case, the second order obstruction vanishes. So it's essentially a vanishing term tensor with some anti-holomorphic part. So we can safely conclude that the second order in closed strings is also vanishing. Yeah, so this means that we can solve the closed obstruction at the closed string equation of motion at second order. Yeah, like this. And what's more is that we only know that right now we only know that we can solve this equation. We don't know what the solution is. So we also want to extract, if we want to know the exact space-time of after this deformation, we want to extract the space-time geometry from this second order solution. The way we do that is to take the inner product of this second order solution to with the NS sector vertex operator. This comes with the metric in the spacetime. So the resulting momentum spacetime field, it looks like this, which you can see factorizes into two parts. And for our explicit choice of vertices, the Wheaton vertex, we can have this normalization constant. And if we decompose the field content into the metric part, the symmetric part, and the B field part, the antisymmetric part, and the allitons, we can compute and we take the field theory limit, we can recover the classical Algebraic-Hansom metric up to a normalization and up to a linearized diffeomorphism. So that's something new because we didn't know that we haven't do it from the string theory, first principle string theory point of view computation. And we also, if we don't take this off-shell, if we don't take this field theory limit, we actually have obtained all the alpha prime correction to the Algebraic-Hansom metric. This is also new, in the string field theory story.
So what is the gauge you chose for the space-time target space?
For the string field or for the target space?
Yeah, there must be. So you try to extract the target space metric and B field. So that depends on the gauge.
Yeah.
So what is the gauge you choose?
We choose we use the Siegel gauge for the string field. And
no, target space.
For the target space, it's just what we compute from this, and you mean the gauge condition for the classical Algebraic-Hansom metric? Or?
Yeah, I'm just asking. Okay, so but it depends on the choice of a gauge, right?
Yeah.
The metric is not a physical observable.
Yeah.
So if you change it's changed under the diffeomorphism. So that's why I asked. So
it's up to diffeomorphism. Actually, if we just compute this, it is not in agreement with the classical Algebraic-Hansom metric. We have to bring it to the similar form, to the classical form using a linearized diffeomorphism.
I see.
I think that's
okay. So up to some choice of the thank you.
Yeah, but we did not realize this diffeomorphism at level of string field theory. We recovered the metric first and then used the diffeomorphism in the spacetime. We didn't, Okay. How much time do I have left? 20 minutes, maybe?
About 50 minutes.
More than 50 minutes.
No worries. So so now that we have a metric, deformed metric of the deformed spacetime in the field theory limit, and of course we can analyze the geometric property of this linearized solution for generic polarization. So we didn't choose this specific moduli. And we find out that no matter how we choose the moduli, it always have the vanishing Ricci tensor and self-dual Weil tensor. And so this means that a generic polarization the space-time geometry is always hyperkähler at this order, which is actually not so interesting story because, as Ivo commented before, the people in phenomenology always want some broken of supersymmetry, but we show that this is not broken, no matter how hard we try, at this order. So it's not that exciting, But the good story is that we obtained some classical results of Algebraic-Hansom metric, and also we can ask a similar story for the cubic closed string obstruction. Maybe if we naively assume the same story for open string, that we might expect some constraints on the closed string moduli. But this is not the case, because if we evaluate this third order obstruction and test it again against the basis of BRST cohomology, we use again the same techniques, except for one crucial difference, that for closed strings, the fundamental bosonic L3 product is non-zero. So for open strings, the bosonic vertices truncated at the second order, but for closed strings, there is non-zero. And yeah, and let's see what happens if we use the same techniques of moving picture changing operators and using the decomposition of using n equals 2 charges. So there are contact terms that contains the bosonic closed strings vertex L3. So it covers the region of 4-punctured sphere modular space that is not covered by L2 vertices. And also we have boundary terms by the same logic. But here the good thing in closed string is that every boundary term that we have can be factorized into homomorphic and anti-homomorphic part. And the anti-homomorphic part is again the same as the open string obstruction. And we have already shown that it has to be vanishing. So all the boundary term vanishes. So we only have to deal with the contact terms. So this is actually the closed string analog of open string field theory with stops, because we have non-vanishing L3. Yeah. And we have shown that if we decompose the third order obstruction by two parts, the first part is the charged resolved propagator terms, and plus the contact term resulting from a 3 product. And the second part is the contact terms that is generated while we move the picture changing operators. Remember when we have the open string story, there are no contact terms generated by moving picture changing operators because there are no M3 product at all. But now we have these contact terms. But if we split again the string field by the n equals 2 R charge, we can show that these two terms actually cancels out because again of the conservation of the U1 charge. So yeah, and what's better is that the boundary terms also vanishes. So the obstruction, the third order obstruction vanishes at all without assuming anything on the modular space. Yeah, it's a more general case as long as we have n equals to supersymmetry.
Okay, okay. But in the open string case, it is not the case. But you're saying that in the closed string case, if you have an n equal to enhancement, there are no third order obstruction.
Yeah, okay. That's what I'm saying. And also you have to assume the regularity of the OPEs so that
already assumed that the first order.
Yeah, for the second order obstruction, it's already assumed, and then you can show that the third order has to be vanishing.
Okay, I see. In the third order case, the 3 vertex operator can collide simultaneously, right?
Yeah.
But so I naively thought that there must be more general constraints, but then in this particular case, there are no additional constraints.
Yeah. The nice thing about this is that the constraints must comes from the localized terms. So
by modular space.
Yeah, in the modular space by replacing the propagator with the projector. While in the third order vertices, there is no at the third order obstruction. There's no propagator in it. So it doesn't contribute.
Yeah. Okay. Yeah. Thank you.
You're welcome. Yeah. So at third order, it is also vanishing. Yeah. So this concludes our story for closed strings. We show that there is no constraints on the modular space. And of course, people will wonder what happens at higher orders, which is harder because we have to evaluate more and more propagators. And but we still have something to say about in the OpenString case, like yeah. Remember in the OpenString case, the string field is defined not only on the boundary CFT, but also on the Chan pattern. It's a tensor product with the Chan pattern space. And if we consider this the parity transformation, and the parity transformation on the space-time, and also together with this transformation on the Chan pattern space, which essentially sends, if we act this on the Chan pattern matrix, it essentially sends the 3, -1, and -1, 3 sector to its opposite. And also, the space-time parity sends the space-time bosons and fermions into its opposite, and we can choose this parity lift to the spin 4, the total spin 4 group, such that it acts on the spin fields trivially, and we can show that this action that we define here it commutes with Q, because Q comes with X times psi, and if it acts on X and psi both, then it gives doesn't do anything. And also for picture changing operators and for the propagators, and also for essentially everything that we need to define the string product. And again, if we expand the string fields as a perturbation relations, we can see that for example, for the fourth order, if we act this pi, the parity on the string fields, then this should all be, if we act pi on this obstruction, then this should be vanishing because there are even number of string fields in the fourth order source term, and each action gives a minus sign, so it should be the same. It should be acting trivially on F4, but it acts with the minus sign on the test state, because if we see that in the test state, maybe I should go a little bit further back. Yeah, in the test state, we have everything comes with a minus sign under this action of parity. So yeah. So this essentially tells us that every even order obstruction should be vanishing. You can think of this way. Let's take the second order obstruction as an example. So we take two cohomological, marginal deformation, which are -1, has the eigenvalue -1, and we take product of these two. So the product should be of eigenvalue 1, but we cannot find anything that has eigenvalue 1 in the massless and the zero momentum sector, because they are all -1. eigenvectors. So it can only contribute to, for example, massive sectors, and essentially the obstruction can only come from at the odd order. Yeah, that's what I'm trying to say. So for the ADHM instanton case, that under this parity argument, we can see that the second order should be 0, which agrees with our explicit OPE calculations. And the third order can be non-zero, which gives the ADHM equations. And the fourth order should again be 0 if this argument works. And if we genuinely want any, for example, correction or modification to ADHM equation, we should look for this only at the fifth order. And there might be corrections to ADHM equations, but of course we know that the ADHM modular space is protected again by the supersymmetry. So these corrections should, instead of genuinely deformation of the modular space, this correction should more, I think, should be think of as a redefinition of fields. So it's just a change of the modular coordinates instead of a real one. Yeah, but the disadvantage of this parity argument is that, again, what helps us is that the closed strings has holomorphic and anti-holomorphic factorizations. That's what helped us a lot. But in this case, it's not helping us because because the factorization, if we act parity on the closed string fields, everything gives essentially the positive parity. So we cannot use this argument. So maybe at the fourth order, there is already some corrections. Yeah, we cannot guarantee that. Yeah, so that's basically all. This is the summarize. So in open string field theory, the equals to localization schemes expresses the cubic obstruction through OPE residues. So the vanishing condition just gives the ADHM constraints. And for the closed string orbifold deformation, this equals to localization together with the factorization of holomorphic and anti-holomorphic part makes the quadratic and cubic classes vanishing uniformly without assuming anything on the modular space. And a special choice of the moduli reproduces the leading Eguchi-Hansen tensor profile. And again, for the higher, furthermore, for the higher order obstruction, for this D-brane system, the parity of the method states might eliminate the even order classes and provided the proceeding order of the equations are solvable. Yeah, that's all.
Thank you very much.